Good afternoon, flag officers, senior officers, delegates, ladies and gentlemen. At the outset, I would like to thank SINGH for giving this opportunity to present a talk on the to this August gathering. Now, in the previous sessions, we have already in the different kinds of alloys and products that could be of use to aerospace and defense industry. During the course of my presentation, I will bring out a brief insight into the role of material in naval application. Now, my presentation will be primarily based on the structural material, that is, the material used for design of ship structures and submarine structures. The scope of my presentation will be as flashed on the slide. Now, this slide presents briefly the structural materials and different other materials which are used in naval application. If you look at it, the ship's hull and the submarine hull are primarily steel based. The titanium, cupronickel, aluminum, magnesium and other alloys are used for pipes, penetrations and other fittings. Aluminum alloys, as ACUM DNR sir already brought out, has also been stressed upon to reduce the top weight or make the ship's top light to increase their transverse stability. So, we have been using aluminum alloys in a lot of our platforms. Composites is the new development, is the advancement that we are looking at. It has got its own challenges, but with the good strength to weight ratio, it definitely gives a great stability to the platforms. Other materials are the cladded steel. In areas where we have different materials which cannot be welded together, or once welded may lead to development of inorganic oxides which can make the material more prone to failure. In such areas, the cladded steel or the cladding technology or the explosive bonding as we call it is also been explored by the Indian Navy. There are developments been done in this field also. Now, coming specific to the structural material for ships and submarines, I would like to briefly touch upon the design philosophy of ship and submarine structures. Now, ships primarily experience the loads due to the weight distribution over the entire length of the ship and the buoyancy, plus the wave loads which are encountered when we put the ship at sea. Now, if we briefly look into the structural design philosophy, the ship over its length has got distributed weight due to the disposition of various equipments, men, articles, etc. And the displacement of the ship provides it buoyancy different at different places due to the different hull forms. So, ultimately we end up into having a bending moment across the ship. This bending moment, when the ship is put into sea due to the rough seas or the waves, is aggravated, and it can be seen in the slide, in the last slide, that bending moment for a ship which is put at sea goes to more than twice to what it was in calm waters. So, this is the nature of load that the ships are going to experience when they are put at sea due to the wave loads. Now, what happens exactly when the wave loads are experienced? The worst condition for the ship structure is when we encounter a wave having a wavelength equal to that of the ship. In such a condition, we will end up into either sagging or hogging scenario. Now, the first one represents sagging, meaning that the wave crests are on the ends of the ship and the trough in the center, resulting in an overall compression on the top part and a tension on the bottom part of the ship. The reverse scenario is called hogging, wherein we experience the stresses in the reverse order as shown in the slide. Now, what exactly happens or what exactly does it look like at sea is represented in the slide, and the material in the center which is experiencing the maximum bending moment could result in breaking of the ship at this point. So this is where the role of material comes into picture. When we have designed a particular structure to a particular scant lengths, then we are looking into a material which can provide us better resistance to the bending. So this is the role of material primarily from the ship design point of view. Now coming to the submarine, it's a completely different ball game. The environment that the submarine experiences is the hydrostatic pressure. The hydrostatic pressure is a uniform distribution of pressure all across the body and increases as the depth of water increases, as all of us know. It is a very unforgiving environment, just like the space. Needless to mention, the recent incident of Titan is testimony to how unforgiving the depths of water can be. Now here I would like to mention as to how we go about designing or arriving at the form of the submarine. Now all of us know that sphere is the ideal shape for any underwater submersible or any underwater body, because it is going to experience a uniform distribution of pressure all around, and it is a structure that will not experience hoop stresses. It is only going to experience a uniform stress all around. But the sphere may not meet the criteria or the requirement of a submarine or a platform, war platform. We need to carry weapons, we need to carry men on board, we need to have propulsion. So sphere may not be the ideal shape or cannot be the ideal shape for a diving platform. So we move to the next possible option, which is a cylinder. But having moved to the cylinder, we have introduced an enemy called the hoop stress. So now with the same thickness and with the same radius, a cylinder will give up at half the depth of that of a sphere. That is hoop stress. So while we have optimized the shape to a cylinder, we have landed with an enemy. So we cannot have a cylinder diving into underwater without knowing that at what depth it is going to give away. In order to regularize that, we start stiffening the cylinder. And when we start stiffening the cylinder, we introduce another enemy called the bending stresses. So once we have introduced bending stresses, we know that when we are diving deep, what will be the mode of failure. Now I will not go deep into this subject because of the paucity of time and the nature of detailing, but I would like to bring out that it is the buckling that becomes the deciding criteria for the overall design of the submarine, and the mode of failure of the submarine is due to buckling. So we are looking at a material which will offer a better resistance to this particular mode of failure, along with a better cyclic life, because submarines are going to dive underwater for multiple times, so they are going to experience cyclic loading of hydrostatic nature. Thus both the buckling loads as well as the cyclic loads are very essential for submarine design. Now coming to the type of submarines, generally this slide gives you a bright insight as to what kind of structures are there in the submarine. Submarines are primarily two types, single hull and double hull submarines. The basic difference between these two types of submarines is the double hull submarine has got flooding space all around it, as can be seen from the bottom slide, whereas the single hull submarine has got floodable volumes in the fore and aft direction. This is the basic structural difference of the submarines. Now coming to the core structures, the pressure hull of the submarine is the one which is designed for hydrostatic pressure. All other structures being freely flooded are not required to be designed for the hydrostatic pressure. So the material of the pressure hull becomes the deciding factor for design of the pressure for the submarine. Therefore, we are looking at a material which can be resistant to buckling and which can give a better cyclic life for a pressure hull design. Now having discussed briefly how the ship and submarine structures are designed, we can just touch upon what are the failure modes of material. Now this is very basic, known to all of us. Materials fail by fracture, fatigue and creep. In the previous discussions, we have already dwelled upon some of these aspects into material development. Creep is not a concern for naval ships and submarines. By virtue of selection of material itself, we can rule out creep. So, we are left with fracture and fatigue. Fatigue can be controlled because it is a process which takes place due to repeated number of cycling. So, we can predict the nature of fatigue of material. However, fracture is specific to a particular material. It is the inherent property of a material, and that is where selection of material becomes very crucial. We need to have a material for our ships or structures which has better fatigue fracture properties, that is better fracture toughness. Now, fracture modes can be ductile fracture, brittle fracture, inter or transgranular. Again, inter and transgranular are of no great significance to the naval platforms by virtue of selection of material itself, but ductile and brittle are very crucial. Now, if we end up selecting a ductile material that fails by brittle fracture, we are in for some serious trouble. We may not be able to predict the material failure at the right stage, as can be seen from the slide and known to all of us, that the ductile fracture usually is more desirable by the nature of its defect. It is predictable and therefore gives the window to the designer to know as to what strengths or to what depths can the platform be designed to. Now, the brittle fracture, the typical nature of brittle fracture is that it is going to be sudden and that it will not let the material go into plastic zone. Thereby, there will not be a deformation region or the deformed region, and the fracture will be all of a sudden. This is something that no naval platform is willing to experience or should be experiencing. Therefore, the materials are selected in such a manner that they are resistant to brittle fracture. They are designed in such a manner that there are lesser stress concentrations which can be achieved by designing the suitable geometry or reducing flaws in the material, and therefore ensuring that the crack propagation happens at a very less rate. Now, having ensured all these properties in the material, the design criteria that we take into account is that the stress intensity factor that is there due to the loading or the environment or the geometry is less than the fracture toughness. Now, we are looking at a material with higher fracture toughness. So, if we ensure that we have a material with good fracture toughness and it exceeds the strength intensity factor in a given environment, we have met our requirement. So, primarily this is what is required, or this is the basic requirement of a naval platform, especially the submarines. Now, having discussed all that, we can broadly summarize as to what all material properties that we are looking at when we are looking into design of naval ships and submarines, and the same is flashed on the screen. The most desirable ones being resistance to brittle fracture, we had discussed briefly, and of course, the isometry in the properties. Now, this is one thing that composites do not provide us or are still under question. So, undoubtedly we land up into steel as the most prominent material for naval platforms. Now, having said that, Indian Navy, as brought out by ACUM DNR sir, has progressed or made considerable progress in developing structural material for naval platform hulls. The steels that we have developed through the assistance of DRDO has yield strengths ranging from 390 to 780 MPa, and these steels can meet the requirement of almost all kind of platforms of the Indian Navy. In addition, we are presently working on development of titanium alloys with Midhani and cladded steel, as I have discussed, with certain private players in the country. Now, this slide represents some of the very commonly used structural steels in the design of pressure hull of the submarine. US rely primarily on the HY80 and HY100 steels for their submarine platforms. The French HLES 80, and as I brought out recently in the year 2022 with the help of DRDO and headquarters ATVP, we have certified and developed indigenously a high strength steel of 780 MPa. Now this is a remarkable achievement in the overall submarine and shipbuilding industry. Now we have a steel which is produced and certified indigenously for underwater platforms. Now there are very, very few countries in the world which are capable of meeting this requirement, and India is proudly in that league now. Now coming to the development of this high strength steel, I'll briefly cover what all goes into developing and certifying a high strength steel for submarine construction. The certification process starts with selection of a steel plant. Now I would like to also bring out to the forum that this development or certification has been done with transfer of technology from one of our close allies, and the process involved selection of a steel plant, then certification of the steel plant itself. In this case it was mostly SAIL, followed by production of manufacturing and testing batches of the steel. Multiple batches were produced, then they were subjected to robust testing, which comprises of nearly 20 types of tests, including that for the steel as well as for the welded coupons of the steel. These tests were static parameter testing as well as cyclic parameter testing. They were tested for fatigue, they were tested for static fracture parameters, they were tested for impact, yield strength, UTS. Some of these facilities did not exist in India, so we had relied on foreign resources to complete the certification testing, and in a span of nearly 5 to 6 years, we were able to manufacture and certify the steel. Now having certified or manufactured the steel, the next challenge was to prepare a prototype of the steel and do the actual environment testing with the prototype. So what we did was, we prepared a prototype of a submarine using this certified high strength steel and then subjected it to hydrostatic pressure, that is an underwater test facility which exists in one of the only places in the world, St. Petersburg, Russia. They are the institute which have the only underwater hyperbaric test facility available with them. So the tests were conducted and the object or the prototype was subjected to the actual number of diving cycles that it is going to experience in its operational life. So the material successfully qualified this hyperbaric test facility testing, and then it was inducted for use in the Navy recently in 2022. Now I can proudly say that we have a steel which can meet the requirement of pressure hull of submarines, which can meet the requirement of the ships and also other underwater platforms like the unmanned underwater vehicles or the extra large unmanned underwater vessels. So what is there ahead of us? We have a steel which meets our requirements. However, the challenges are many. We can still have a steel of higher yield strengths. I think DRDO is already working on this front to develop steel of yield strength up to 1000 MPa. Composites, as we had discussed, are the future. They have their own challenges, but notwithstanding, future lies in composites, so they cannot be ruled out. Some of the other interesting technologies that have come into picture or are being worked upon are the biomimetic hull. You might have heard of this. This is a hull form that resembles the shape of a marine mammal or marine animals. So we have a hull form resembling the shape of marine animals, means it will reduce the underwater noise, it will improve the hydrodynamic capabilities, thereby improving the range and endurance. So this is one field that is being worked upon by various advanced countries. Composite propellers, Russians have done a lot of advancement in the field of composite propeller development, which is going to increase the overall efficiency and underwater noise and signature of the propellers. The next one is sonar cancelling hull form, not proven but published by Chinese that they are capable of producing sonar cancelling technology, thereby mimicking water. Now what happens interestingly is, in our submarines we have something called as the rubber tiles, which are coated all over the outer surface of the hull. These rubber tiles are of the thickness of 50 to 80 mm. The primary requirement of these rubber tiles is to cancel or absorb the high frequency noise or the high frequency sonars which are emitted by the enemy submarines. Now interestingly, the thickness of the rubber tiles decide that what wavelength frequencies can it cancel. For example, we know that when we have a high frequency sonar, its wavelength will be smaller, and vice versa. When we have low frequency, the wavelengths are larger. So while the thickness of the tiles is limited to 50 to 80 mm, when the wavelength of the sonar exceeds 80 mm, then the rubber tiles are of no more use. So there comes this technology which is called the advanced tiles by the Chinese. Now these tiles are able to absorb the active sonars, low frequency sonars, and they are able to produce opposing sonars which will cancel out potentially the sonar and mimic the shape of water, meaning that it will depict that there is nothing in water, it is just pure liquid. So this is very interesting development by the Chinese and could drastically change the entire geopolitical scenarios if it comes into force. So these are some of the developments which are happening in and around the world in terms of material and advancements in technology. Of course, the material developments come up with its own challenges. Some of them are highlighted in the slide. I had discussed that we are already working in-house on development of high strength steel. But once we have a structure made of high strength steel, the welding becomes equally challenging. The strength, the increased strength of the steel brings along with it hydrogen embrittlement. Now while we will be able to produce high strength steels, but will we be able to weld it efficiently to produce a quality marine structure is the big question. So the welding technology for high strength steel is something that needs to be discussed and developed. This is one gray area. Similarly, composites, we are all aware of the brittleness and anisotropy associated with composites. These are being addressed by various advanced countries in the world and still remain a challenge to be completely dwelled upon. The third thing is titanium. We are aware that titanium is one material because of its high strength to weight ratio is preferable for submersibles. However, the welding technology for titanium is known to very few in the world. A small example of that is in the year 2022, James Cameron dived deep into the sea with Deep Sea Challenger. Interestingly, the pressure hull was made of titanium, but it was not welded, it was a bolted structure. This Deep Sea Challenger was bolted because Americans did not have the advanced titanium welding technology available with them. So this is the nature of challenge that titanium welding poses, and it's something that needs to be looked into or is an area of interest definitely to the Indian Navy. Now these are some of the properties comparison which are known to all of us between the composites and metals, which makes it which helps us decide as to what nature of material should be selected when we are going for structural steel. Now two, three things which are of interest to us here are the directional property, which limits the composite use for deeper vessels, especially submarines. The stress strain behavior, it is purely elastic. We need a material that is elastoplastic so that we can predict and design structure to desired strength. The third thing is the cyclic strength. Needless to mention that submarines are going to dive deeper and longer number of times. So we need material that can have better cyclic life. With that, I would like to reiterate on the Titan issue that we had faced recently. Although a lot of advancement have been made in composite development, especially by Russia and US, the recent incident of Titan still poses certain specific questions in our head. We are aware that the Titan dome was made of titanium, whereas the cylinder was made of composite. It was a carbon reinforced fiber, and we know what happened when it dived deep. So, with that perspective and question, I end up my presentation. Thank you very much for